particularly quantum chemistry and atomic bonding, because bonding is the basis of molecules, right? Why do atoms bond together? Why do they stick together? Well, you need this sort of theory to understand bonding, because I was talking a bit earlier in a previous session about lobes. This kind of thing, like the wings of a dragonfly. This is where those wings come from, and depending on the shape of these wings. And what are these wings? They're the probability distribution of finding the electron at certain angles, theta and phi, relative to the nucleus. Okay, and depending on the shape of those wings, if you have a hydrogen molecule, H2, hydrogen nucleus 1 and hydrogen nucleus 2, and if they have lobes and so on, they will bond as a function of the shape of the lobes. So if you have other atoms, like the two atoms that bond, if they're a different kind, they may have different shaped lobes, so they will bond differently. So chemistry and hence our existence, because we human beings, we're just a bag of molecules in a sense, right? So understanding chemistry is critical to our existence. All right. So here are some early, the smaller values, low order, for small values of L and M. So you could calculate these if you like. You've got enough knowledge now to actually calculate what these terms are. So here's the expression for the spherical harmonic y of 1 naught. So L is 1 and M is 0. And here's for L is 1 and M is plus or minus 1. Remember that M, it's limited in its range depending on L. So M is less or equal to L and greater or equal to minus L. Okay, so if L's 1, M can range between plus or minus 1 and naught, of course. Right? So you have three expressions. You have 3 spherical harmonics for L is 1. Okay. Now, so for L is 2, M can be 2, 1, naught, minus 1, minus 2. So I have 5. You'll have 5 expressions, 5 spherical harmonics for L equals 2. And here's what the spherical harmonic is for y equals 2, and M is naught. It's this. And here's what it is for L is 2 and M equals plus or minus 1. And now you notice these. I guess when this is 0, there's no phi term. When it's non-zero, you get these phi, e to the I phi terms. Okay. And here, when L is 2 and M is plus or minus 2, you get a bit more complicated expression. So sine cos here and sine squared, and it's these terms that give you the sort of lobe, wing shaped. Now, what are these things? Don't get lost in the details. Keep the bigger picture. What are these? They are eigenfunctions, right? They're wave functions. And so from the Born approximation, you get a probability distribution by squaring them. Okay. So if you square these things now, take the absolute value. In other words, these exponentials drop out, right? Because if you take the modulus of e to the I something, the modulus is just 1. Okay. So if you square these things, you can forget about these exponentials here. So you just get these terms with the thetas involved. So let's actually draw some graphs of these spherical harmonics, and they'll depend only on the thetas. Okay, so here it was just a constant, right? So so just a circle. Here's your z-axis. So depending on your m, remember what m is? M is the allowed. It's the eigenvalue for the z component of your angular momentum. So you can, and what's theta? Theta is the angle from the vertical, the z component. Okay? So if you're looking, what's the value of these spherical harmonics? Let's say at angle theta, that theta would be defined to be that. Okay, so this angle theta is the angle from the z-axis. Right. So if you're talking theta 0, you're here. Okay. So these things are called polar plots, and all they are is just you mod this and square it. Right? Just here. So you're modding and squaring the spherical harmonics, and that will give you the probability distribution of where the electron is. So presumably here's the nucleus, right, at the center here. So here for L is 0, well, it's just this simple expression. So you just get a spherical symmetry. Right? So the electron, its probability distribution is spherically symmetric. But, and we're dealing with that case earlier, but now with bringing in angular momentum, you get more complicated probability distributions. They're not spherical now. They're now sort of lobed. You call these things are called lobes, right? So you get this kind of thing. So for L equals 1. Well, I've just drawn two of them. So this is what it looks like for m is 0. Your cos theta, right? So when theta, I mean, you can deduce why it's like this. When theta is 0, you get this. The cos theta is 0, just 1. So your value for y here will be root 3 over 4 pi. So here, this value here is square root of 3 over 4 pi. Now when you go to 45 degrees, you're about here somewhere. Okay, so cos of 45, 1 over root 2. So this times this, so it'll be something smaller. So about here. And when theta is 90 degrees, okay, cos of theta is nothing. So you're here, right? And so on. So you get this sort of figure of 8, with two lobes, okay, lobe, right? Now, when L is 1 and M is plus 1, we haven't given the minus 1 case, but L is 1 and M is 1. L is 1 and M is 1. So you get this sine. All right. Well, when theta is nothing, sine of it is nothing. And when theta is 90 degrees, sine of 90 degrees is 1, so it'll be maximum, so your lobe will go this way. It'll be a figure of 8 in that orientation, and when m was 0, figure of 8 sort of in this orientation. So you can sort of sense why these lobes look the way they do. And it gets more complicated. Like when L is 2 and m is 0, L is 2, m is 0. You get something like this, and now you start getting like these little lobes here, right? It just comes out of the mathematics. If you plot this, you get a computer to plot it for you for different values of theta. You'll get this sort of how do you describe it? It's starting to look a bit like a flower, right? These double lobes, big ones and small ones. And if L is 2 and m is plus 1. L2 plus 1. Now you get this cos theta sine theta stuff, and you get, it looks like a 4-leaf clover now. And if L is 0 and m is 2, So you get this kind of stuff. Looks somewhat similar to this, right? And next session, is to run out of board, but for next session I'll continue with these pretty patterns, these as they're called polar plots. Right? I'll do it for L as 3. I'll give you 4 more diagrams, 4 more polar plots. All right, well, I'll stop there.